everybody. My name is Dale Kim. I am a software engineer at Unity, and I work with the DOTS team in Burbank, California. Welcome to this introduction on Unity.Mathematics. So one of the first questions you might have is, what is Unity.Mathematics? And it is a shader or SIMD style math library. So if you've used HLSL or done SIMD programming before, it should be very familiar to you. And when I say SIMD, I'm referring to single instruction, multiple data. Now, we won't go over SIMD in depth in this talk. However, one of my colleagues, Andreas Fredriksson, will be giving a talk called Intrinsics, Low-Level Engine Development with Burst on Thursday here at Unite. So I encourage you to check out his talk. So Unity.Mathematics implements very basic vector and matrix types. So like 3-dimensional vectors, 2-dimensional vectors, and they're provided in terms of float n. So like float 2, float 3, float 4. It gives you quaternions, and it gives you things for matrix 3x3s, 4x4s, things like that. Additionally, it provides elementary math functions that you might have found in, say, the C runtime math library. We're talking things like min, max, absolute values, trig functions, normalizing vectors, all sorts of stuff like that. Now, we've covered the basics of what it is, but when would you want to use Unity.Mathematics? Well, if you're already using the data-oriented technology stack, well, you're using it now, because the entities package, the Unity physics package, they both make extensive use of Unity.Mathematics already. So you might not be using it directly, but if you're using DOTS packages, you are using it under the hood. Furthermore, Burst is aware of Unity.Mathematics, and that's a very key point that I'll come back to later on in this talk. Another big reason why you might want to consider using Unity.Mathematics is for determinism. What do I mean by determinism? Determinism is when you want to compute a floating point number deterministically across multiple platforms. As it stands now, if you compile your code for an ARM device or an Intel x86 device, the floating point code generation is not necessarily guaranteed to produce the same result. However, in the future, the Burst team is planning to add this kind of support, so that way you can deterministically come up with the same results across multiple platforms. This can be very useful for things like networking, where if you have, say, a synchronized lockstep network multiplayer, then you can rely on every machine computing the same results. Another big reason is because of performance, and we'll get back to this later, but Unity.Mathematics can often beat classic Unity. And what I mean by classic Unity is all the things that are not Unity.Mathematics, all the things that you would do today, vectors 3, vector 4, matrix 4x4, things like that. An equally valid question is when not to use Unity.Mathematics. Well, you might not want to use Unity.Mathematics if you currently depend on extremely specific behavior of today's Unity. There are certain functions which are implemented in a particular way, and you might have an equivalent version of that function in Unity.Mathematics, but you're not guaranteed that they are going to produce the exact same bits. So they might give you close enough values, but they might not be the same values. In those cases, you don't want to switch. Now, another reason is if you make heavy use of UnityEngine.mathf, and there's a lot of basic functions in there, but there are also some utility functions in there which Unity.Mathematics currently does not have an equivalent version for. If you make heavy use of those functions, you either need to port those functions in mathf and create your own versions using Unity.Mathematics. But if you're not willing to do that, then it might not be a good idea for you to switch to Unity.Mathematics. Another big reason is if you depend on existing libraries or plugins that expect everything in classic Unity's vector 3, vector 4, and matrix 4x4s. You could, in fact, use Unity.Mathematics now and then just convert out to that when you need to interface with those libraries, but that might not buy you that much, and it might not be worth your time to do that. But let's assume for now that you're already sold on Unity.Mathematics and you just want to get started. How do you actually get started? It is available now. You can just go open the package manager, search for mathematics, and it'll show up, and hopefully you can see that. And then once you find it, you just click install. Once you click install, it's available in your project today. Once you have it installed, you can go to whatever source file where you need it and just type in using Unity.Mathematics, and then you can go ahead and start writing code. Now, you want to write code, maybe you don't know where to start. Well, I'm going to present to you 6 small examples, which I would expect almost every game to want to do. They're very basic examples, and they're meant to illustrate what you might already know how to do in today's Unity and how to do the equivalent version in Unity.Mathematics. It should introduce you to the style of Unity.Mathematics, and it will also highlight some common pitfalls that you might have when you first switch over to Unity.Mathematics. First example. Componentwise vector multiplication. Componentwise vector multiplication here means you have 2 vectors, you got x, y, and z components, and say you want to multiply the x components together in each vector in the result. That's what we're doing here. In today's Unity, this is how that will work. You create 2 vectors, and the first vector is 2, 4, 6, and 8. The second vector is 1, -1, 1, -1. And then you call vector4.scale with these 2 vectors. That gives you the result of 2 times 1 equals to 2, 4 times -1 equals to 4, or -4, 6 times 1 is equals to 6, and so on. Okay? This is the component-wise vector multiplication. Unity.Mathematics is very similar. Instead of creating vector 4s with vector 4, you now say new float 4. That is the Unity.Mathematics type for a 4-dimensional vector. And the constructors are basically the same. You just use the new type name. But the main difference here is that instead of calling a specific function, you just call operator multiply. This will probably be surprising to some of you who are not used to this, but this is very common in SIMD-style code, where all of the basic operations, when you call the operator versions, they operate on component-wise on each individual component. They don't do the mathematical operation that you might expect. So that is something that you should definitely watch out for when you first switch over to Unity.Mathematics. Example number 2. Building a 4x4 matrix. Every game's got matrices, so it would be good for you to know how to build one. In today's Unity, it's very straightforward. You just create 4 vector 4s. Each one represents a column in your matrix, and then you just feed in those vectors into your matrix 4x4 constructor. Very simple. Unity.Mathematics is also very simple. You basically just replace vector 4 with float 4, matrix 4x4 with float 4x4. It's very straightforward. Unity.Mathematics also provides different constructors where you can provide just 1 float value, and then it'll just go ahead and set all 16 elements with that same value. Or you can have a version where you have 16 float values and just set every single one individually to whatever you want. Example number 3, operator multiply with 2 4x4 matrices. In classic Unity today, in this example, we have a matrix 4x4, and all its elements are set to 1. The second matrix is the half-identity matrix. When you use operator multiply, that performs matrix multiplication. So it's effectively just going to scale the matrix of all 1s by 0.5. Okay? In Unity.Mathematics, the result is very different. If I have the same values in my matrix of all 1s, and then a half-identity matrix on the right, the result is, in fact, the half-identity matrix again. Okay? Now, why is this? Remember, operator multiply is, in fact, component-wise multiplication. So the first element in the matrix is multiplied by the first element in the second matrix. Okay? So because the half-identity matrix, the upper triangle is all 0s and the lower triangle is all 0s, basically the only elements that survive from this first matrix are the ones on the diagonal, and you just multiply all those by 0.5. Okay? This is perhaps one of the most common places where people get tripped up when they first implement things in Unity.Mathematics, or if they port old code over to Unity.Mathematics, because often you just have the asterisk in there, you just copy paste, and then you think it's going to be fine, but in fact, these are very different operations. So you need to watch out for that. Example number 4 is you want to multiply a 4x4 matrix and a 4D vector. In this example, we have a 4x4 matrix on the left and a vector 4, so like a column vector on the right. And all you have to do is just call operator multiply, and that works out just fine. And that implements the 4 by 4 times a 4 by 1 to give you a 4 by 1 vector. Okay, that is the matrix vector multiplication that we all expect. Here in the comment, though, is another line which doesn't compile unless you write your own code. But if you were to write this, you have a vector 4 on the left and a matrix 4 by 4 on the right. There is no such operator where it takes a vector 4 and a matrix 4 by 4. This is just not implemented. You could write your own, but it's not provided by Unity by default. How would you do this in Unity Mathematics? Well, we don't use the operator multiply anymore. We instead call math.mul. That implements matrix and vector multiplication, so we can just give it the float 4 by 4 on the left, a float 4 column vector on the right, and that just implements the 4 by 4 times the 4 by 1 to give you a 4 by 1. That's fine. The second line is the commented out version that we couldn't do before in classic Unity. But now we have a float 4 on the left, a float 4 by 4 on the right, and this implements a 1 by 4 row vector times the 4 by 4 matrix to give you back another 1 by 4 row vector. Now, you have to notice here, so this F4, it's a float 4. The concept of a row and a column vector, they're not distinguished in terms of the type. It's up to you to understand what the convention is and make sure that you use it appropriately. This lets you just put the float 4 wherever and get what you want, and you don't have to worry about a second type, but it does mean that you have to be a little careful if you don't want to be willy-nilly about where you put the float 4 in this operation. Example number 5, quaternion multiplication. Let's say that you want to rotate, you have some orientation and you want to alter that orientation by rotating about the up axis, right? I want to rotate by 45 degrees about the up axis. Well, in classic Unity today, here's one way that you could probably do it. You find the up axis, and then you just call quaternion angle axis. You provide the angle in degrees. You provide the axis you want to rotate around, and that gives you the rotation quaternion Q. Okay? These next few lines here, it's just me making up some current orientation. So I'm just going to call quaternion.Euler and give it a 45, 90, 180 degree rotation. For me to rotate this current orientation around the up axis by 45 degrees, I do Q, the rotation quaternion, times the orientation. It's very easy, just use operator multiply. Unity Mathematics, it's slightly different, but the basic form is the same. The first thing is that we currently don't have the nice convenient like vector ups, vector left, vector forward. We don't have that. But it's very simple to just define your own up vector here. So we defined our axis. And we now call quaternion.axis angle. Don't ask me why it's axis angle and not angle axis. It's just the way it is. But you provide the axis. And the first thing to notice is that we call math.radians on 45. Almost every single angle in Unity Mathematics expects everything to be in radians, whereas classic Unity, it's almost all degrees. So you should definitely keep this in mind when you first use anything with angles in Unity Mathematics. Once I have this, I have the rotation quaternion Q, as before, and I'm setting up my current orientation that I just made up, and it's a very familiar function. We have Euler, it's basically the same. I give it the rotation in radians. And then instead of using operator multiply, I have to use math.mul. Operator multiply is not going to give you the result that you want. You have to call math.mul to perform the actual multiplication operations with two quaternions. Example number 6, generating random numbers. This is also a very common place where people get confused at how to generate random numbers in Unity Mathematics. How do you generate random numbers today? Well, it's actually very easy. You just access the static property, Unity Engine random value, and that gives you a random float in between the range of 0 and 1 inclusive. Inclusive. That's very important. That means that you can get the endpoints 0 and 1 are possible to be returned. Let's say that you don't like 0 to 1. Well, we have a way that you can provide your new min and max range. And again, you just call random.range with your min and max range, and it will give you a random number in between that range, also inclusive. The inclusive part is very, very important, probably, if you care about randomness in your game. How do you do this in Unity Mathematics? The first biggest difference is instead of accessing some global static property, you instead have to maintain your own state, your own random number generator state. You do this by doing new Unity Mathematics random, and you give it a seed of your choosing. It's up to you. It needs to be non-zero, but that's fine. Just pick one. And then once you've newed this up, this is your random number generator. This might seem a little strange, but it is in fact advantageous in two main respects. The first one is if you're running in a parallel context, you get to control much more explicitly how different threads might access different random number generators. And this can be very important if you care about having a deterministic result in your game. The second main reason is now that you can create your own state, it's very easy for you to separate random number generators for different parts of your game. So if you have like a loot game and you have damage also, maybe you want to have a random number generator for figuring out when you do a critical hit. And then you want to have a separate one for generating loot. So for those reasons, it's very nice to have this explicit state set up. But how do you actually get a random float? It's very simple. Just take your random number generator state and call next float. That gives you a random number between 0 and 1, but the maximum end of the range is exclusive. You can never get 1 back as a result from this call. So, people who are doing loot generating games, this can actually be very important. So you'll want to pay attention to this. Similarly, if you want a different range, you can supply your own, and it'll respect that range, but the max end is again exclusive. You cannot get that number back. So hopefully that was a good taste of the things that you might run into when you first use Unity Mathematics. If you're going to port code over, it should be pretty obvious that a direct copy and paste probably won't work. If you have very small sections of code, that might work, but you're going to have to change type names, obviously, but the biggest things that you should look out for are matrix vector operations, radians versus degrees, and random number generation. These things are all actually very different, so you do have to pay attention. If you do decide to port, say, classic Unity code to Unity Mathematics, it will be very, very useful for you to keep the existing code around as a ground truth. Don't just go ahead and convert, and then let's say, oh, I did a great job, delete all the code, and then start running it. You don't want to do that. If you can, try to keep both versions alive and just have an if check. If using Unity Mathematics, use the Unity Mathematics version, and then play the game a little bit. Keep it around. And then if you encounter a bug that you didn't see before, just go ahead and change that Boolean and just say, using Unity Mathematics false, and then it'll just dynamically switch to the old version. If the bug goes away, that's probably a good sign that there's something in your Unity Mathematics implementation that needs debugging. So having that around is very useful. So you try to keep both as long as you can until you're quite confident that your new version is what you want. Another big thing is that replicating exact results is not always required. A real issue that came up last week was that a customer had said that they switched over to Unity Mathematics, they're comparing the actual float values of their quaternions, and they see that the Unity Mathematics version returned the negated version of that quaternion that they expected from the classic version of Unity. That quaternion actually represents the same rotation, but their tests were looking for exact equality between those numbers, and so of course the test said that you failed, but the quaternions were in fact representing the same thing. The other thing is that oftentimes the results are just slightly different, and you might not actually notice, but if you do an exact equality comparison, it might fail that test. So don't get too bogged down on trying to get the exact same results. That's actually not reasonable to expect. But take it as an opportunity to just switch over to your new implementation and see what you get. If you are writing Unity Mathematics code and you're still relatively new, find all, go to symbol. These things are all your friends. All the source code to Unity Mathematics is fully available. So you can search through all the text. If you're looking for matrix multiply, you can just start typing out MUL, and hopefully you'll find it. If you want to find something else, start typing stuff out and see what you find. If you can't find it, well, then you can go ahead and ask us, and we'll probably be able to help you out. So I said earlier that we would go back to performance. Performance is a very, very big deal to us. And so I was very curious, how does classic Unity and Unity Mathematics, how do they stack up? So the thing that I did was 1 million of the following 4 tests: vector 4 additions, matrix vector multiplies, matrix matrix multiplies, matrix inverses. Just run those with Unity Mathematics, with classic Unity, try it on a mono build, try it on IL to CPP, with and without burst. What are the performance numbers? This is how classic Unity compares, and these numbers are probably not that meaningful without any context, but the blue bars are with a mono build. So this would be basically, you're in the editor and you hit, play mode. That's that kind of a build. IL to CPP, it's a standalone IL to CPP build, so it's compiled to machine code. Mono and burst. This is if you're using dots and you have the burst compiler enabled, and that's, you're getting bursted machine code, and you can, in fact, use classic Unity with burst. That might not be obvious, but that is possible. And then there's IL to CPP with burst. And the biggest thing to just notice is that for each one of these tests, going from mono to machine code, any compiled version, it's significantly faster. So unless you have a really good reason to deploy a game using mono only, I highly encourage you to compile the code. And then there's Unity Mathematics. Yes, those blue bars are embarrassing, I guess, but we'll get into that later. Yes. If we go back a little bit, so notice that super tall bar here, that's 1600. If we go back, this one was 160, so that's 10 times slower. So it's like, what's going on there? Well, let's take a closer look at each test. Vector addition. Blue is classic Unity, and orange is Unity Mathematics. Here, things look kind of even keel. Mono is, it's fine. It's 25-ish milliseconds. IL to CPP is significantly faster. It's like twice as fast. And then when you move on to burst, it gets even faster. Okay? And that will be the general trend for all of these. When you look at the burst numbers, though, at the end, you can see that classic Unity is actually slightly faster than burst. This is something I want to investigate and figure out why. But the difference is really small. Like, you have to remember that this is 1 million vector additions, and over that million, there's a 0.4 millisecond difference. So in any real game, you will probably never, ever notice. Round 2, matrix vector multiplication. Again, the compiled code is faster than mono, and now we're starting to see a trend where Unity Mathematics just dies when you use a mono build. Okay? It will become obvious, if it's not obvious already, that using a mono-only build in Unity Mathematics is a very bad idea. Similar to vector addition, burst with Unity Mathematics is just ever so slightly slower than classic Unity. That is something that we have to investigate, because we would love for Unity Mathematics to be the same or faster, but it's only slightly slower. So I'm not sweating too hard about that one. Matrix multiplication. At this point, just ignore mono for Unity Mathematics. That's not what Unity Mathematics is built for. But we finally get to a point where Unity Mathematics is now handily beating classic Unity when you use burst. So, classic Unity is 13.1 milliseconds. Unity Mathematics is at around 10. So it's a big enough difference. You'll still probably never notice in your game, though. Round 4, matrix inverse. Again, mono, don't care about that for Unity Matrix. We'll get to that later. But we're finally at a point now where when you compare classic Unity and Unity Mathematics using burst, where Unity Mathematics wins by a landslide. It's a massive difference. Or what is that, like 6 times faster? I can't figure it out, but it's faster. okay? So who is the winner? Unity.Mathematics, maybe? Classic Unity only wins when you use mono, okay? However, when you use compiled code just destroys mono. So please use compiled code as much as possible. But one thing is lingering in my head, and possibly yours too. What's going on in this matrix inverse case? Why is it that suddenly burst is winning? Let's take a look more in depth. Here's what the graph looks like when I throw out the ridiculous mono runtime. And so straight from the start, classic Unity is much slower. You know, if you're using an IL to CPP build, Unity.Mathematics is in fact 2.75 times faster to do 1 million matrix inverses. Why is that? The reason is because in classic Unity, when you do a matrix inverse, it is in fact implemented in C++ on the engine side, and it is implemented with Gaussian elimination. When you do Gaussian elimination, you're like picking out individual elements in your matrix and trying to figure out like how do I eliminate these rows, and then how to do that inverse. That is in fact very branchy. It's very difficult to vectorize or have SIMD code gen for that, so it's actually quite slow. Unity.Mathematics, however, uses a very different implementation. Unity.Mathematics, taking advantage of this property with matrix cofactors and matrix determinants, you can basically compute the entire matrix inverse directly with no elimination involved at all, and it can be done with SIMD code gen, which is the main reason why you see this massive difference here. But then, looking at just Unity.Mathematics, if you look at IL to CPP versus a burst build, even there's a 3 times speed up. You might think, it's all compiled code, like why is it so much faster? Shouldn't all machine code be the same? And the answer is, in fact, no. You can have very different results even with compiled code. This is a snippet of some burst assembly for the matrix inverse for Unity.Mathematics. I don't expect you to sort of like read all of it and understand what's going on. That's not the important part here. The important part is those first 4 lines up there, that is simply loading the 4 columns of the matrix into CPU registers. Gets the data out of memory, puts it into registers. Once it's there, I've elided some code in the ... but it shuffles some data around in registers and then gets everything set up to do the actual inverse. And then here in the center, there's all these math operations. This is, in fact, what the matrix inverse operation is. That's how it's implemented in Unity.Mathematics, and this is the code gen for that. The biggest thing to note is that everything here is SIMD. You can tell because the CPU instructions at the end, they end with PS. It stands for packed single. And so everything is working on 4 floating point numbers at the same time, and it just crawls right through every instruction, no branching, nothing. And then at the end, we store the result back to memory where we expect it, and then we can use that result. This code is awesome. It is fantastic. This is what I want to see in the IL to CPP version. However, when you actually look at the IL to CPP assembly, it looks very different. Different enough that I have to sit there and think and like, what is this code doing? I actually still don't know that much about what it's doing. I didn't have enough time to dig in. But the main questions that I have here are, why are we storing values to the stack in the middle of the inverse? Like in the burst version, we just read it out from memory once, did everything in registers, then wrote it back out. That's it. But here, in the middle of inverse, we're just looking at the stack for some reason. That's very puzzling. The bottom section of the code, it's like, why are we reading from the stack? Presumably it's because we stored something to the stack and we needed to read it again later. But then the other big thing is if you look at these multiplications, additions, the mul SS, add SS, the SS is scalar. Scalar here means it only operates on 1 floating point number at a time. So that right there is 1/4 of the performance you could possibly get. Okay? So clearly this code is less optimal than the burst version. But why might that be the case, right? Like, here is a snippet of Unity.Mathematics code from the inverse. And the variable names here, that's not the important part. The important part here is the code is very small. You just have 3 float 4s. You're doing 2 matrix or 2 component-wise multiplications and a subtraction. That's it for every single line. It's very compact, very small. This is the IL to CPP version. So you've taken your C# code, which, back here, the C# code. We take the intermediate language, the IL, and we generate equivalent C++ code. It might be a little tough to see, but in these comments, these are the original C# code that we had. But all the stuff in between, that's C++ code that was generated to implement exactly what was in that comment. And so the amount of code has just exploded, okay? Imagine you feeding this into your C++ compiler and hoping that it'll figure out what you originally tried to do in your C# code. Like, you can kind of imagine that maybe it won't be able to do the same thing. So what's the point? The point is that Unity.Mathematics and Burst, in fact, work very closely together. Burst knows a lot about what Unity.Mathematics is. It has lots of specific intrinsics. And so it doesn't lose context like IL to CPP does with whatever C++ compiler that you end up using. When you go through IL to CPP, you're kind of trying to figure out what the original code did, but you've already translated 2 times to something else. Data types and operations, which map directly to CPU intrinsics, will if you use Unity.Mathematics and Burst. If you write your math code in a SIMD style, you should get SIMD code gen. If you don't, we are very interested in hearing about it because we would love to make sure that that always is the case. But one big thing to note is that it's not like a magic thing. Like, just because you use Unity.Mathematics and Burst doesn't mean that all of your code is going to be super fast SIMD code. There's a lot of things that can break SIMD code gen, and one of the biggest things is how you access your data. If you're constantly poking at individual vector elements and doing things with single elements, you're never going to get the SIMD code gen. So I went through a bunch of graphs. What does this all mean? If you're using only mono, don't use Unity.Mathematics. Unity.Mathematics was simply not designed to be used with mono. When you use Unity.Mathematics with mono, it's doing all this like emulation of CPU, basically CPU instructions on the virtual machine. That's always going to be slow. That's what Burst is for. Burst is to make sure that you get exactly down to the fastest machine instructions possible, knowing what Unity.Mathematics is doing. If you use Burst or IL to CPP, for Burst, definitely use Unity.Mathematics. For IL to CPP, it's probably a good idea. So I'm coming to the end of the talk. What's the main things that you should take away? Unity.Mathematics is available today. You don't even have to be using dots to use it. But Burst makes everything much, much better. Like, really don't use Unity.Mathematics without Burst. If you're considering switching to Unity.Mathematics, there's 3 main questions that you should ask yourself. The first one is, how much performance critical code do I actually have in my code base? If most of your time is spent in a bunch of math, this is probably a thing you should consider. Another question is, do I want to port old code to use it? Say that I have a giant code base and I'm already using vector 3, matrix 4x4 left and right. Do I want to move all that code over to Unity.Mathematics? Probably not if you have a giant code base. If you have a tiny game and your code is small, then maybe it's good for you to actually switch over. You're able to take less risk because you have so much less code. Another big question is whether or not you're going to use dots in the future. If you know you're going to use dots like next month, you probably should just get started now. If it's not in your future plans, then you might want to stay away for now. Really, Unity.Mathematics you want to be using with the rest of our dots packages. If you are already using it, we would love to hear about your experience so far, what you're doing with it, what problems you ran into while trying to write your first code, performance numbers. We'd love to hear about that too. And so now we're at the end. If you have any questions, feel free to ask. Basically now, we have a microphone in the back here and back over there. So if you have any questions, go ahead, just ask. Or you can find me outside later, or you can email me. You can find me on Twitter. All that. Thank you.
Hi, I have a question. So, Unity.Mathematics is slow with mono, right? Right?
Say that again?
Unity.Mathematics is slow with mono. That's what you said. Now,
yes.
if I have a project that doesn't use burst, but I use IL2CPP, right? Then I will get fast math in the build, but it will be very slow in the editor, right?
I believe so. It's tough to hear you. I'm sorry.
Oh, is it better now?
Yes, it's
All right, so far. So, as I said, it will be fast in the build, but very, very slow in the editor.
yeah.
Yeah, so,
Yes.
What if it is unacceptable? Like, how to deal with this situation? Do you have any plans how to fix this?
That's tough. That's tough to me. I'm not sure that I even got the full question. So what was that again?
Oh, yes. Sorry, I will say again. If I use IL2CPP
Yes.
in the build, then my math is going to be fast. But at the same time, it's going to be very, very slow in the editor.
Oh, I see. In the
Yeah,
editor.
so do you plan to address that in any way?
Yes, that is true. So like if you jump into the editor, it could be in fact quite slow. So that is something that you'll have to be very careful about. If you spend a lot of time jumping in, play mode in the editor, this might also be a bad idea for you to switch. Right. If you use burst, that's no longer a problem.
Okay, thanks.
Any other questions over there?
So I'm using a lot of native code. Can you tell me if alignment will be a problem? So can I still use my unsaved copies, or will this not work with Unity Mathematics?
So you're just talking about just copying the data back and forth?
Yes.
That should be fine. That should be fine.
So flow 3 will not suddenly use 32 times 4 bits in memory.
No, it should not. That one's a little harder for me to answer because I don't know exactly what context. Usually in Unity Mathematics, most of the code that we have, you're like stuffing them into native arrays, and we know exactly how big those arrays are going to be. So you can rely on the fact that it's going to be, 3 or 4, however many, each single precision float is going to be 32 bits.
Okay, thank you very much.
Mm-hmm.
Hello. For now, you normally used when you wanted some deterministic randomness, and with an object behind it, you would use system.random from the .NET namespace. Would you normally now just use the Unity random generation?
I'm not that familiar with the system random, but yes, if you want it deterministic, and you use Unity Mathematics random, yes, you will definitely get deterministic results, assuming there's no other non-determinism somehow poisoning it.
Okay, but you don't have an exact comparison of Unity Mathematics random and system random.
No, I currently don't.
Okay.
But if you're curious, I believe the current implementation of Unity Mathematics random is on XOR shift.
Okay, thanks.
Hi, I have a question about. Do you support double precision and CMD instructions?
Yes, so there are in fact double 2, double 3, double 4. There are like double versions of all the types that I've shown. And I do believe that it will do the double SIMD code gen 2.
Okay, thank you.
Mm-hmm. Any other questions? All right, I think that's it. Thank you for coming.